happens if you...
Circle.
What do you mean it goes in a circle?
It's
if you pick x1...
x1, say, like...
Here. If that's x1, can you find an x2?
Yes.
Yeah, there's x2. But where's x3 going to be?
At x1.
Yes, exactly. And x2 is also going to equal x4. So the point is, are you ever going to get closer to anything? No.
Keep going.
Yeah, and there are other functions that this happens with, but sometimes you get stuck. What's interesting about inverse tangent, as far as I remember, is that no matter where you start, you will get stuck. No matter where you start, you will get stuck on this. You'll keep on going around. x3 will always equal x1. There are other functions where there are specific points where this is true. There are other functions where you can get stuck going in a circle, but not. But as far as I don't want to say, I can't think of one right now. But I strongly suspect there are functions where you can get stuck in a circle, but not everywhere is what I'm saying. Not everywhere. Does that kind of make sense?
Yeah.
Okay. Use Newton's method with the specified initial approximation x1 to find x3, the third approximation, to the root of the given equation. Now here's the thing. We could do this out where you find the equation every single time. You don't quite need to do that. What's the only thing you really need to find?
The next number.
Well, we need to find f prime of x, right? You have to find the derivative, correct? What's it going to be? 3x squared plus 2, correct? And do you remember what the formula was for x sub n plus 1 to x sub n minus x sub n prime of xn? Correct? That's what they want you to use. So the question is, so if we want x2, that's going to be x1 minus f of x1 over f prime of. So that x2 is going to be 1. Well, no, x1 is, so yeah, it is 1. I'm sorry. 1 minus what? F of 1
Negative 1.
over. I'm just writing it at all the steps just so you see it, right? So it's going to be 1 minus, and you plug in 1 into that. What do you get?
Negative 1.
1 plus 2 is 3. 3 minus 4 is negative 1. You're absolutely right. All over, plug 1 into this, you get 5. So you end up with 6/5. Then to get x3, and we'll skip a few steps here, it's going to be 6/5 minus f of 6/5 over f prime of 6/5. At this point, it might be helpful to use your... Anybody get this? What'd you get, Maddie?
1.55.
Yeah, what'd you get for x3? Yeah. She got 1.625?
1.17.
Okay, hold on. You guys are killing me here. Bill, what is it?
1.5797.
Okay, the 3 decimal places. How many people got that? Nope. Anybody get this, the 3 decimal places?
1.179.
179 like this?
Yeah.
Yep. 1.179, that's correct. Now here's the thing. You really, this is supposed to be without a calculator, right? But the thing is, you're supposed to go to 3 decimal places, and this isn't really a nice one. So on these Newton method questions, when you have a calculator, you're not using it to find a 0, because that's not really not going to help you, because you need to get to 3 decimal places. This is not supposed to be the actual 0. You're never really going to get to it. You could quickly get very close. Exactly, right? So how do you use your calculator to quickly find these x values? What do you plug into your calculator? Let's try that.
The equation and...
You can just hit enter again.
Well, we need to put in that value right there, right? So what do you do?
Enter
y3 evaluated at the answer.
Exactly. So what you do is second alpha, like this, y3, evaluated at, you do parentheses, second answer, right? We do enter. What do we get? Boom.
And you hit enter again.
Well, no. Well, look. Ready? Second entry. Enter. There's the next. You see how it's getting really, really close, right? Second answer. Sorry. Second entry. Enter. Look at that.
Can you just hit enter again?
Yeah, you can. Woo, sweet. So look at this. This method has gotten us down to what they think is within 10 units of accuracy, right? So let's go back to the original graph, though. Let's go to the graph and see what this is going to graph really slowly, right? Do you agree with? You see why?
Yeah.
I'm going to quit this for a second here. Actually, I don't know if I can. No, it's really not going to like that, because it has to do a lot more math to do that third one. So it's doing that third function, which is kind of neat. Okay, there we go. Hold on. I'm going to turn it off, okay? I'm not going to graph that third one. I'm going to go back here. Let's graph this thing. So there's the original one. There's the... Well, fine. It just takes a little while, okay?
Go faster if the calculator's...
Why use the actual, like, computing power of the calculator. I don't of
Why does
the.
it have this? Why does it have the
Because it
specification
probably
of something from the?
It's purposely
70s?
crippled. Yeah, the 1970s exactly. Okay, so ready? I'm gonna graph the original function. Yay! Here it is. Done. Okay. Done. All right. Let's see what the calc function gives us. Second calc. Let's calculate the 0. What's it ask you for? A left bound, and then it asks you for a
Right.
right bound, and then you give a guess, and then you press enter. Do you know what it uses? What method it uses?
Newton's
It
method.
It pretty much uses Newton's method, pretty much. And look what it gave us. Is that pretty much identical? Yeah, it absolutely is. So when you do this out, you end up with a really nice way of doing this. So that's a way you could do it on your calculator pretty quickly. So what's really cool about this? What's really cool about this method is, let's look at the screen for a second here on y equals. Let's say we wanted to do this with a different function.
You just change
All you have
it.
to change is the first line.
That's
All you
awesome.
have to change is the first line. And then you can start with whatever initial value you want. So could you easily program this into your calculator?
Yeah.
Yes. Look up the programming language. Go ahead and do that.
Although if we had access to our calculator in the test, I'm not even. You just like
Type it out. Yeah. Well, no. That's what I'm saying. That's why I think you don't need a program to do this because you don't know where it could go
You
wrong.
just put in the program and
Yeah,
then do second calc.
Exactly. But tell everybody, when x equals 3, we know that the tangent line is. What's the equation of that line?
5x minus 4.
Minus 4. If Newton's method is used to locate the root of the equation f of x equals 0, so find where it crosses the x-axis, and the initial approximation is x1 equals 3, find the second approximation. Find the second approximation. So x2 is equal to x1 minus what? F of x1 over f prime of x1, right?
Yep.
So x2 is going to be equal to,
3.
what is x1? 3 minus
F of 3.
f of 3 over
F prime 3.
f prime of 3. And what is f prime of 3?
5.
So 5 times 3 minus
4.
4. So x2 is going to be 3 minus f of 3 over what?
11.
11. Now the question is, can we go any further than that? Can we go any further than that?
No.
Why not? We don't know what f is. This thing could do anything. So,
You could have like plus a billion on the
exactly, right. This thing could be really, really high up. Do you understand what I'm saying here, everybody?
Mhm.
So can you go any further than this, do you think?
No.
No. So x2 would be 3 minus f of 3 over 11. Find the second approximation for x2. Do we know what this point is?
No.
Yeah, well, we can. We can find it.
Oh, wait. What is that point? We know it's 3 comma what? 3 comma 11, right?
Mhm.
Correct?
Yeah,
So we're trying to find out where this crosses the,
x-axis.
this value right here, sorry, I gotta do a different color here, that is x2, right? That value right there is x2. Do you agree?
Yeah.
Where the tangent line?
Yeah.
Right? So what could we do? How do you find the x-intercept of a line?
Equals to 0.
How do you find
You
the...
set the equation equal to 0. and
Thank
solve
you.
for x.
Thank you. Now we'll record. So x2 is equal to 3 plus 1/9. So 3 1/9. That's great. Right, great. That's actually, I'd imagine that's pretty close. Now here's the thing. They want to go to 8 decimal places. So what are you really going to have to use?
Your calculator.
Let's go back to what we already have plugged into our calculator. And instead of this, what are we going to write? X cubed minus 30.
Yeah.
We'll go back to here. And let's just see how accurate this was. It was y3, right? And y3 at what? That was our first one, right? 3.11111111107. What is that?
3 and a 9.
That's 3 1/9.
No, enter. You can just hit enter.
No, because it would do it at 3
Your
again.
second enter will just bring up y3 to 3, and then you can just put
Oh, just put answer. I'm just going to do that right there. Okay, I'm going to do it once. Okay, so now we hit enter.
Yeah,
We hit it.
again.
Hit it again. Hit it again.
Yay, you got it.
It didn't change. So how quick was that?
It was
That's pretty quick. So that was, this one was the second one. It's like 3 times. It got there really, really, really quickly. Let's clip this in. So we think that's accurate too. 8 decimal places. It's pretty good. Let's actually do it on the calculator. Let's do 30 to the what power? 1 divided by 3, right? What does that come out to be? Look at that. Now here's the thing: is our calculator estimate keeps going, but it seems as though our estimate is as accurate as how the calculator is doing it, and we did it pretty quickly. So if you wanted to do this next question right here, estimate the 7th root of 1,000, what would you be finding the 0 of?
X is 7 minus 1,000
Equals
0. So it's the exact same.
It's the exact same process, right? I bet this one is going to be. Why do I think this is going to be even quicker? Well, it actually depends on how fast it gets there. It depends on 2 things: one, the function, and your initial guess, right?
Yeah.
The 7th root of 1,000. Let's just say 3 again. It's not 3. The answer isn't 3. It's irrational, okay? 1,000 doesn't have a nice 7th root, right?
It's gonna be some really low, like 1.
It's going to be really small, right? It's going to be really small. But let's start at 3. The thing is, why does this function potentially go there faster than x cubed?
Because the number is smaller.
What does x cubed? What does x to the 7th look like compared to x cubed? Use words.
Explodes.
No, it
No.
doesn't explode.
It stays more
smoother.
compact to the x.
It's more
intercept.
compact. It's steeper, right?
Yeah.
So maybe the slopes of the tangent lines, maybe that affects how fast it goes to 0. Let's just check this out. If we do y equals, we change this to x to the 7th minus what? I'm not graphing this. And then what do? We do this, y3, and we do it at what? Our initial guess is 3. Okay, so that's not bad. Hit what?
Second enter.
Like this?
And then you can just
Oh, this go back to this. Second ants like this.
Yep.
But then I have to close it, so about the same.
reserve it.
Enter. And then what?
Enter.
Enter. Enter. Is the same. Oh, it stayed the same, right?
No.
No,
That-
just
that-
on the last one.
Did
Digit.
right there. Here we go. That's good. That's even more. So let's raise this to the 7th power and see what it is. Bingo! Is that pretty cool? I think that's pretty cool. I think that's very cool. So anyway, now do you basically have a method of estimating any root without using the root function on your calculator? Yeah.
Or at least you know how it does it now.
Well, I think we're pretty sure this is how it does. It probably does some version of this. There might be some way. Usually, there's like the fast method for Newton's method. You know, there might be some way of it. But the thing is, the calculator just generally it just does an algorithm. It's not a thinking. It's not really a thinking machine. The first thing we'll do, let's do one of the functions we already did. So let's do x to the 3rd minus what was it, 30, right? Now the question is, you need to know what the formatting is for you go to math, and it's n deriv right here. N deriv, and as far as I remember, it's going to go the function you want. Let's actually pause this. Let's just look at this up instead of me just. So there it is. Okay, and then you have to do comma, and then you're differentiating with respect to x. So, and then what value are we doing? X again. If you went back to the main screen right here, look, if you went back to the main screen and you hit math, and you went down to n deriv, watch, n deriv, vars, y vars. I highly recommend using y1 and y, like plugging in the function as one of the y values, because it's really annoying and dangerous to type out. You can type out the whole function if you want to, but be careful because you have to put commas in the right place. So then we do comma, and we want to do it with respect to x, and we want to do the derivative at 2. Let's say we just want to evaluate it at 2. We can press enter on this, and it tells you the derivative evaluated at 2 is 12. And is it doing algebra? No. How do you know it's estimating there?
Because it's not
0, 0, 1. It's not doing it exactly. So if we want to go back here and we want to graph this, there it is, to x. And then what would our y3 be? It would be x minus what? Yep, vars, y1 of x, right? Divided by what? y2 at where? X, like this. We good so far? So let's quit out of this. Let's quit out of this, and we call vars, y vars function, and it's y3, right? And what was our initial guess for the cube root of 30? 3, right? We do it once. Oh, look, 3 and a 9th. And then we do second entry, but instead of 3, what do we put in there? Our answer. We do enter again, enter again, enter again, and look what happens. It comes out to be the same thing. So I'll do that screenshot right here. So we do y3 at, what's our initial guess going to be?
1.
1. Enter.
Oh boy.
-2 all of a sudden, right? So then let's do the same thing. y3 evaluated at what?
Answer.
Second ants. Exactly. And we press enter. 4. -8. 16.
Everyone,
What's going on?
it's going exponentially large.
It's going away from.
Ah.
What does the cube root of x look like when you graph it?
How do I graph it?
What does it look like? Let's graph it and see what happens here. I'm not going to actually... Let's see. So let's just graph it. Zoom standard. What does this thing look like?
That.
It looks like this.
It looks like inverse.
It does, right? But here's the thing. When you start taking tangent lines, it's going to get farther and farther away. It doesn't actually go towards it. So actually, here's another one. It doesn't stay static.
Because the slope gets so small that
Whoosh! It just keeps on going out. Exactly. On this one. So if you graph this, look what happens. We'll just do a quick diagram. We take this. Whatever value you choose on x cubed, on the cube root of x. So this right here is y equals the cube root of x. If you take this, it goes over to here, and then it's going to go even further. It keeps on going further and further and further and further. Yay! Oh no.
There's a question asking us to find the astronomical.
On this question, you're absolutely right. So on this one, what am I in right here?
Radian.
I'm in radian, yeah. I mean, it will just change maybe how quickly it approaches if you think you're plugging in pi when you're really plugging in 3 degrees. Which
Sure, it doesn't really matter.
it doesn't really matter, but
But it,
the approach might change. It might go berserk or not work. It might break. You just need to be like in the neighborhood.
when she had in degrees and she was getting 0.4.
Oh, really?
0.499.
Oh, cool. Interesting. It gets stuck.
Show like if you would try.
Try it again.
Yeah, try
Okay.
again in degrees.
Cool. So let's just stay with radians, and we're good. Okay. On the AP test, you're in radians. On the AP test, you're in radians. I don't want to say that 100% because they can do. Yes, unless it says like it's in degrees. That was recorded. Great.
Yes.
Okay. Pause. You're like, okay, f prime of x is 2x plus cosine x, right? So in order to find that absolute minimum, you need to solve cosine x is equal to. You need to solve for that, right? You're setting it equal to 0. Here's the thing. Do you know how to do that?
No.
No. You have an x inside a trig function and
Outside.
not only outside, but outside on another one. On the other side. Well, not other side. It could be on the same side. But the point is, you have x inside and outside of a trig function. Do you really have any algebraic tools to attack that? No. But now you do. You have a way of estimating it pretty accurately using your calculator.